the church got against these ideas. So Copernicus said, well, you see, I am presenting a model here. This was the preface to his book, which is only a pure hypothesis. It is worse than the previous model. That is what was said in the preface to the book on the orbits of heavenly objects. So, later, much later, 1 century later, it was found that Copernicus did not write the preface. The book was published on 24th of May, 1543. That was also the day he died. He didn't know what was happening because he was dying of cerebral hemorrhage. Some assistant or student of his, just to avoid unpleasantness, put this unnecessary preface. Nevertheless, the Copernican system was still very clumsy, as clumsy as the Greek system, which he tried to change. He had all the same cycles or circles and epicycles or circles on circles, all the Greek baggage he maintained. All that he did was interchange the sun and the earth. And then we come to early 16th century. But before that, the Copernican model, some people noticed, did explain one or two things which the Greek model did not. And that was the fact that the planets Mercury and Venus always appear close to the sun. If the Earth were at the center and the sun and the planets were going round, then sometimes when the sun was setting, Venus could be rising in the opposite direction, 180 degrees away. Why not? Independent motions. But that never happens. Venus and Mercury are always very close to the sun. You can see them only in the morning before sunrise or late evening after sunset. Never at night, for example. With the sun at the center, that is easily explained, because there is a limit from the sun to which these two inner planets, Mercury and Venus, can approach. Similarly, it also explained, for example, the retrograde motion or the opposite motion of Mars. For example, Mars seems to be moving most of the time from west to east very slowly. This is not the rising and setting motion. But occasionally it moves in the opposite direction. And that is slow. That motion is slower, retrograde motion. With the sun at the center, that is explained. This is the Earth, this is Mars. So at this point of time, the Earth, being closer to the sun, moves faster and actually overtakes Mars, which is on a parallel track. So when it overtakes, it appears to the Earth that Mars is going backwards. During this period, retrograde as it is called, Mars appears brighter. Now, obviously that happens when the Earth and Mars are closer. At a position like that, there is no such effect. Mars won't be so bright and it would be appearing to move as usual, west to east. So the Copernican model, however clumsy, did have one or two small advantages. And therefore, this was the accepted model with the sun at the center and the various planets going around, and finally the stars. This was the situation in the early 17th century, that is about 60 years after Copernicus. And that's when Johannes Kepler came into the act. Kepler was around 1600 at a place called Uraniborg in Sweden, where he was assisting a great observer called Tycho Brahe. And he was a very good assistant. Now, shortly thereafter, Tycho Brahe died, and Johannes Kepler, he inherited all the data that Tycho had obtained. Well, Tycho had a peculiar theory. He said, well, the Earth may be going around the Sun, but the Sun goes around the other objects. It was a hybrid theory which nobody took seriously, and least of all Kepler. But Kepler had great respect for Tycho Brahe as an observer, if not as a theorist. And he found immediately that there was a problem with the planet Mars. The theory, that is, the theory with the Sun at the center and the planets going around, and the observations of Mars did not match. There was a small discrepancy of about 8 degrees of arc. It's a very small amount, and one could have said that this is nothing but observational error. However, Kepler had so much faith in Tycho Brahe's observation that he said, no, it can't be an error. Rather, he wrote very boldly that this small discrepancy will show the way for a complete reformation of astronomy. And that's how, in 1608, Kepler finally, after trying frantically for 10 years to close this gap, he finally broke with the past. It was the first great leap forward. What did he do? He said, well, I've tried so many circles, circles upon circles, circles upon circles upon circles, all sorts of things. But this gap of 8 minutes for Mars is not going. So out of sheer desperation, after nearly a decade of work, he said, all that work is wrong. Let me try something new. Let me try an oval orbit, elliptical orbit. And immediately he found one that fitted the orbit of Mars beautifully. And of course he could find ellipses for all other planets as well. Next slide. Suddenly, the universe had become very simple. Not all those sphere upon sphere upon sphere upon sphere. What those people were doing for 2000 years, non-stop activity was somehow try to approximate an ellipse by a series of circles. Instead of 2000 years effort, if they had given up the idea of the circle as being perfect and thought about other shapes, then astronomy would have begun progressing 2000 years before it did. So Kepler came forward with his 2 laws around 1610. The first was the planets go around the Sun in an elliptical orbit with the Sun not at the center but at a focus. The second law was the motion of the planet is such that the areas which are swept out in equal intervals of time, that is, let us say, this is the area swept out in 1 month. This will be equal to the area swept out in 1 month, but at a different place. So you have 2 different types of triangles, but the areas are the same. Now, there's a common sense justification. If the planet is closer to the sun, it moves a little faster. If it is farther away from the sun, it moves a little slower. So this was the second law. And then suddenly people started beginning to see light. However, there was one more law that came later, about 20 years later. Kepler wrote a book. He was a great writer, and much of his writing was nonsense. And so also his latest book. It was called Harmonis Mundi, the harmony of the worlds. And in that, he spoke so many things, harmony and music and all sorts of nonsense. But in the middle of all this was his third law, which says that, the distance of a planet from the ellipse or the mean of the ellipse bears a definite relationship to the time the planet takes to go round. It was as if the universe settled down perfectly. After Kepler, in fact, within the same 17th century, Sir Isaac Newton was born on Christmas Day. And he was reading all these things about Kepler and all. And the question had come up. Why Kepler's laws? Why all this strange behavior? And Newton started working on it. And to cut a long story short, he realized that what was happening was, there was a force between the sun and the planets, which we today call the gravitational force. And the force goes according to the inverse square of the distance. You will see these things later. Even Kepler had thought of something similar, but for Kepler it was something like a magnetic force that became weaker and weaker with distance. So Newton came forward with two independent theories. One, the universal law of gravitation. Now this again was a major step. Newton could see that this law would work. It would work. But it would work for planets in the solar system. From there he made a giant leap and said it works everywhere in the universe. And then he came with the next theory, that was his laws of mechanics, which all of us do in school. The first law, the second law, the third law. Once he had all these things, he found that with the universal law of gravitation and his laws of mechanics, he could easily deduce Kepler's laws. So Kepler's laws were nothing more than another expression of Newton's laws of gravitation and mechanics. So this was the picture of the universe. The sun at the center, the various planets going round in orbits. Now there was no more nonsense of crystal spheres and all that. These objects would remain like that because of the gravitational forces and mechanics. And beyond the solar system, there would be all those stars. So that was the Newtonian universe, where the constituents, where the building blocks of this universe were stars. The sun being just one star, but there being thousands, hundreds of thousands of stars in the universe, all at different distances from us. It so happens that we belong to the solar system, which is a part of the sun. Next, please. This picture continued for almost 200 years, more than 200 years, till the early part of the last century, when giant telescopes were built in California, Mount Wilson and Mount Palomar. A 200-inch and a 100-inch telescope were built there. And there was one astronomer who used these new telescopes with a great degree of success. He was Edwin P. Hubble of the Hubble Space Telescope fame. Now, when he looked through his huge telescopes, he was in for a shock. The Newtonian universe, which lasted barely 2 centuries, compared to the Greek universe, which lasted for 2000 years, even the Newtonian universe seemed not to be the whole story, because Hubble saw a number of cloud-like objects, patches in the sky, which we call today galaxies. In those days, they were called nebulae. Nebula means nebulous, cloudy. So people thought they are just clouds. And they were reasonable in thinking like that. But what Hubble did was, he could resolve the cloud. It looks like a cloud, no doubt. But through this large telescope, it turned out to be a collection of millions of shining dots of light. Not a cloud at all, having a structure and millions of stars. So Hubble realized that the universe was far more profound than what Newton had thought. The universe is made up of such clouds or extragalactic nebulae, as he called them, or today galaxies. Each galaxy containing something like 100,000 million stars. And Hubble could find millions of such galaxies spread all across. So the building blocks were not the stars, they were really the galaxies. Next. Here is another galaxy. Notice that they all have, not all, but most of them have a very peculiar spiral shape, which is of course because of the dynamics, the various forces which are there in and around galaxies. So millions of such galaxies. Later you will see in a little more detail, these are spiral galaxies, but even here there are nuances, barred spirals, irregular galaxies, and so on. These galaxies are all strewn across the universe, forming the building blocks. But Hubble went one step further. He observed these galaxies spectroscopically. This is the light which we obtain from galaxies when the light passes through a spectroscope, which is nothing but a prism and a sort of a telescope. Now, this object appears very bright, which means it is quite close to us, it is nearby. And see what the light through a spectroscope is like. You are seeing some dark bands, dark lines. These lines are actually quite close to your left. The left is actually the blue end of the light spectrum. Here, this object is fainter. and these dark lines are a little more distant to the right, towards the red side of the spectrum. So this is called red shift. This is even fainter, that means even farther, and here the lines are even further towards the red, more red shifted, and so on. So Hubble realized what this means. The dark lines and their shift is due to the Doppler effect, which you can encounter even for sound. If a car which is speeding passes by you, or a train for that matter, with the full horn, then as the car passes you, you will find the sound gets distorted. So that's the Doppler shift, and the same explanation here. So Hubble had a brilliant interpretation and discovery. What he said was, the greater the distance of the galaxies, the faster they are moving away from us. The light reaching us from those galaxies is getting more and more red-shifted. Here are the lines for an object that is very bright, because it's very close and the lines are near the blue. But by the time you go to an object like that, these lines would be in the red region, because that object would be moving faster. So Hubble proposed his law that the speed of precession is proportional to the distance. The greater the distance, the greater the speed with which the galaxy recedes. Now let's play this in reverse and see what happens. Today the galaxies are at a certain distance, but they are expanding very fast. They are all rushing away. So tomorrow they will be even further apart. Day after, even further apart. And so on. Reverse the time. Today the galaxies which appear at a distance were yesterday closer, and the day before even closer, and the day before that even closer. So if you go back in time, it is very easy to calculate. Today's figures, roughly around 13.5 billion years ago, all these galaxies were at one point, which today are so distant. They all started off from one point. Presumably, at that point, there was a huge explosion, which we call the Big Bang. So that is the theory that got built up. By the time Newton's work was completely overhauled with all these new inputs, we then come to, well, I don't have to tell you who this is. Einstein, a cartoon drawn by a very famous astronomer called George Gamow. Have you heard the name of George Gamow? He was the man who finally said the universe is exploding. So he drew this cartoon of Albert Einstein to explain his theory of general relativity. And according to that theory, light also interacts with gravitation. So if light passes close to a very massive object, light will get bent, just like every other object. And what really you are seeing is the sketch of an experiment which was proposed. The sun is here. When the sun is here, you can't see a star. anywhere near. But suppose the sun has been eclipsed, then here is the star. However, light from the star, by the time it reaches your eye, would have bent because of the gravitation of the sun. And so, to you it would appear that light is coming from that direction. Dotted line. In other words, during a total solar eclipse, if you take a photograph of the sky, nearby stars, nearby to the sun, they would appear to be higher than they actually are. This is a gravitational bending of light. That was one of the important consequences of Einstein's theory of gravitation. And this was observed in 1919 by Sir Arthur Eddington. So, again, a nice drawing by George Gamow, the same George Gamow, giving the main formula of general relativity. And his idea was that general relativity is the Taj Mahal of all the temples of knowledge built by man. So this was the Big Bang, when all the matter was at one place and it exploded. And the matter started rushing out. And as the matter was rushing out, it collected and formed galaxies and then stars and so forth, the entire stuff. This is the Big Bang theory that was a product of the last century and is still accepted. But the question that the Big Bang puts up is, okay, the galaxies are all rushing away, but what will happen tomorrow? What will happen day after tomorrow? Will they keep on going away? Usually, when there is an explosion, you find that the objects go up to a certain point. Gravitation is acting against them, so they stop and then they fall. So what about the universe? It's just an explosion like that. Will all the galaxies go expanding more and more and more forever? Or our common sense tells us, will they slow down as they go up, come to a halt, and collapse again? This was the accepted model even as late as 1997. It's called the standard Big Bang model. However, that year I suggested something different, that no, the universe won't stop and collapse, it will go on expanding and accelerating. Why? Because while gravitation is there, no doubt, there is a new type of an energy which we today call dark energy everywhere, and it is this dark energy which keeps pushing the matter away and away, faster and faster. And this was observed within 1 year in 1998 by 3 separate astronomers from California and 1 from Australia. And so the dark energy universe was the new paradigm that replaced the older ideas. However, this also raises certain rather inconvenient questions. I won't go into all this in detail. And that is on the very nature of space-time itself. So far, all the theories have been built on the assumption that space-time is like a continuous, beautiful cloth. Take a silk cloth, very smooth, very continuous. But look at the cloth through a microscope. What will you find? It is anything but smooth because it is made up of threads, some going in this direction, some going in that direction. So it is smooth from a distance, but as you go closer, it is not smooth. Similarly, space-time also, unlike what Einstein and all the others have thought and are thinking even today, it is not smooth, but it is like this, like a net with holes and gaps in between. That is not an easy idea to digest because now for 4,000 years we have been thinking that space-time is smooth. Then comes another idea as a corollary to all these ideas. So far, we thought that galaxies or clusters of galaxies are the building blocks of the universe. Now comes the idea of multiverses. Our entire universe itself is a building block, and there are millions of such universes or multiverses. That is truly mind-boggling. It's difficult to go to this level of imagination, but it is not science fiction. There are some scientific arguments at the base. We don't know. The whole point is that verification, which is at the heart of science, you have to verify. You can't say that this is Newton's law. Why? I don't know why, but you accept it. You can't do that. You have to argue why Newton's law, because we have observed it. So here, verification becomes next to impossible. So you can see that starting from a point where the earth was at the center of the universe, floating like a flat island in waters, surrounded by all these objects. That was essentially the Greco-Babylonian thinking. We have come a long way indeed. Here, you would have noticed, at least those of you who attended the previous public lecture, that this is not the Indian view. It is like a parallel branch to which we today belong. The ancient Indian view was very different. But that is totally a different story. So, any questions or comments?
Can you just please elaborate what is space and time smooth? How do I comprehend that actually?
Well, it's easy to imagine they are smooth. That means, if there is a point of space, to put it very crudely, very easy to imagine that you can go to a point very, very close to it, as close to it as possible. But suppose I tell you that, no, you can get close to it, but not as close as you want. Beyond a point, there is a gap. There is space here, space there, nothing in between. Very difficult to imagine. That is what it means, a sort of a discreteness in the universe.
So, does that give us from existence of multiverse? One, that space-time is not smooth. Is that the reason why?
Not really, but the reasons are slightly different. The reasons are when we are going so far away, there is no logical reason to assume that the universe in this 13.5 billion years, that this is the limit. Yes, it is a limit, no doubt, of a certain sort. It is the limit of our observation. But from there, uh, some people say that let us not assume that it is the limit of the universe, it's the limit of our observation. Right. Yes.
What do you mean by multiverses? Is it like,
Pardon?
what do you mean by multiverse? Is it like the same,
It may be different. I mean,
or it's like you are breaking the space-time continuum and it is
yes,
like
yes.
multiverses?
That is being broken in any case. It's a different space-time altogether. With different laws. Think of it as parallel universes.
Sir, how did the people come to a conclusion that the earth was round?
Others?
Round.
Well, there are so many even elementary exercises. Like, this is the standard example. When a ship is coming towards us, first we see the topmost point and then the bottommost. Vice versa, when it is going away from us on the ocean, first the ship disappears, last of all, the topmost point of the mast. Then, if you look at the lunar eclipse, what's happening during the lunar eclipse? What's happening is the Earth's shadow is falling on the moon. If the Earth were a square block, then the shadow would also be rectangular. But the shadow is always circular. So there are such, or even for that matter, the Eratosthenes experiment. You take a stick, shadow of the stick at one place does not have the same length as the shadow of the stick at the same time on another place because of the Earth's rotundity.
Big Bang is set ఎలా వచ్చింది సార్?
That nobody knows. There are limits to which science goes and operates within these limits. But beyond these limits, it is no longer science. That's something else. It's
Until
like
and
you go
unless it is
to
explained.
cross the border, go to Pakistan, it is no longer Indian law. Some other law applies there.
That's where the God comes in.
The early observers, the early observers in the Greek time, how were they able to determine the distance of a star from a planet? Is that
Stars from the planets.
Yeah.
That's very easy. The planets
Stars blink.
move through the stars. And of course, that's true. The stars blink because they are so far away. Planets don't blink. But the main thing is the planets move through the stars. The word planet means wanderer in Greek.
Are the holes in space and time like an intrinsic property of the space right from the beginning, or did they form because of the expansion of the universe?
Well, it's a good question. The answer would be that the holes were there from the beginning. If there are holes, if space-time is indeed not a continuum, then that would be a property right from the beginning. There would be slight differences maybe at the time of the Big Bang now, but essentially the main property would be the same.
Sir, stars don't move.
Stars do move and move very fast. But this is the movement within the galaxy. And they are so far away that this movement cannot be seen. In some cases, it can be seen from historical records over a few thousand years.
Space, according to the Big Bang theory, space was first concentrated in a particular position, then it explodes.
The universe was at a point.
Yes, so how can you say that it had holes right from the beginning? Maybe the holes were formed because of this.
Shortly, when we say beginning doesn't mean exactly at that point, but very shortly there. And how very shortly? Even that scientists have a small idea about that. It is 1 by 1 followed by 42 zeros. That means that fraction of a second. 1 by 1 followed by 42 zeros. That fraction of a second.
So is space-time like is it limited or is it creating itself more and more?
According to the ideas that were in existence till 1997, it would be limited. But today it is no longer can be said.
Yeah, if you are saying that there is a dark energy which is actually allowing it to accelerate,
Yes.
then that means maybe your Big Bang theory itself is not correct.
You mean to say universe is
So
expanding?
there might not be a Big Bang. If you are calculating it backwards, you might say.
Well, so far the indications are there
Big Bang
was
theory
some
is
sort of what is called a singular event. But you may be right, in the final analysis,
But still today it is accepted, no sir? Big Bang theory is still today accepted.
Is
Nobody
there
has
by the
come
vast
with
majority.
Nobody has come with another theory.
No, there are a few other theories, but they are not partakers.
Was there a time when there was absolutely nothing in the universe?
Can nothing come from, I mean, can something come from nothing?
You know, these are all metaphysical questions. No longer a domain of physical science, but of philosophy and speculation.
What
But-
are
Then what is
the
the God part interpretation we are talking about?
Oh, that's one of the many points, and but it's important because it gives mass. Or so it is thought.
other theories apart from Big Bang theory?
You see, one theory that was popular up to a certain point is what is called the steady state theory. No Big Bang, nothing. Just expanding space.
The
And in the
galaxy.
meantime, matter is created out of nothing. So, as one galaxy disappears, in that time, let us say, to put it very simply, another galaxy is formed from nothing. But that has, Narlikar and all the Fred Hoyle Narlikar, they were all for this theory, but today not many takers. But the reason I say even Big Bang today will have to be looked through lenses. When we talk about multiverses and so on, where the entire universe is a unit, then the Big Bang as the starting point for the universe itself becomes a little suspicious. So there is some fresh and new thinking, but nothing concrete as yet.
You said that the Big Bang theory was the building block for this universe. Can this, apply even to the multiverses, like all of those?
You see,
Like, can our universe be one of those
yes, these are all highly speculative but possible. There is no direct evidence. You see, our physical science depends on direct evidence. If there is no evidence, then it will not be accepted. So there is no direct evidence for these things. That doesn't mean that they are not possible.
What is the evidence for
For Big Bang
multiverses?
theory, yeah. What is the evidence that was there that it was
For
accepted?
the Big Bang theory,
Yeah.
Hubble's law and all these things are indicative of the Big Bang theory. The way the galaxies are rushing away from each other.
How much of the fact was made into fiction in Interstellar?
I have not seen it.
Because it is too, what should I say, too imaginative or
Generally, these science fiction stuff, they give you what you want to be, or what you would enjoy seeing. That's the reason I do it.
You said the galaxies are moving away from you. So be located in that place right now?
According to the steady state.
But that's, we have not known it yet.
No, we don't believe in the steady state theory as such. Anyway,
Okay, so time by time we'll see best galaxies in space.
yes,
Observation.
but today there is a new element that has been observed, namely dark energy is there. We talk about dark energy, nobody knows what it is, we don't even have a good characterization of dark energy. But that changes the game. We can no longer talk in terms of the old ideas, that galaxies are rushing away, therefore it will be empty space. No. Now there is dark energy there, so we don't know.
సార్ ఇన్ని గెలాక్సీలను నడుపుతున్నది బిగ్ బ్యాంగ్ శక్తినా సార్?
Yes. Big Bang and today we'll say dark energy and all that are energizing the universe.
Sir, actually, can we actually understand what actually is Big Bang? I mean, by word it means something else, but is it?
Mathematically, it means a space-time singularity out of which the universe has emerged. At that point, we don't know. But even a little after that point, we know.
They say that in space-time, it is just 1 minute from the Big Bang till now.
Not really.
No?
There is something called time dilatation and time contraction. But these are units of time which we give.
So who came up with the idea of multiverses and why is it so widely
Well,
accepted?
recently, this is a recent development from 2 or 3 angles, one of which is string theory, where you have what they call the landscape of universes. The other is an argument put forward by David Deutsch, another free-thinking physicist, and also from a different point of view, that if there is a singularity, like the Big Bang, very instant of Big Bang, then it's like the North Pole. If you are exactly at the North Pole, would you know which is the west, which is the east, which is the south? West, east, south, all these directions have a meaning a little away from the North Pole. Even if you are 1 inch away from it, it has a meaning. But if you are at the North Pole, no. So it could be any. So with these space-time singularities, the universe that emerges, why should it be like this? It could be like something else. This is like saying we are just away from the North Pole and we have gone to the east. But why east? It could be west.
So basically, multiverses is just to compensate for the probability of the result.
Yes, there are many arguments, but essentially these people feel that it is too narrow to think in terms of a single universe. There are so many other possibilities.
Sir, singularity theory means there was no space, no time.
At that instant, a point where all the laws of the universe break down. So
No, only if there is laws, then it will break down. Sir, that
at that point there are no laws.
yeah, there was no question of breaking.
So that's a singularity. So thank you very much. And your next meeting, you will discuss and you will decide.
Thank you, sir.
Thank you.
First, your attendance, please.
One second.
Maunika. Srujan. Sri Harsh. Aparna. Krishna. Tanay. Pranav. Bhavyasri. Rahul Sai. Aishwarya. Kundan Abhishek. Lata. Fani Rao. Sri Kalyan.